Well, this is the last of 3 videos looking at acyl substitution. Just to kind of review, we looked at the formation of carboxylic acids, the class 1 carbonyl that we can make all of the other class 1 carbonyls from for acyl substitution reactions. We looked at the synthesis of carboxylic acid. Looked at really just 2 reactions, and there are others, but these are 2 that are prominent. Carboxylation of Grignard reagents, where a Grignard reagent was added to CO2, and then hydrolysis of a nitrile or a cyano group in strong acid conditions with water. We could take a CN triple bond and convert that to a carboxylic acid and ammonium cations. And then in the first video looking at acyl substitution, we looked at the 2 most reactive class 1 carbonyls, the acyl chlorides and anhydrides, or acid anhydrides. These we said are fairly sensitive to just even water, acyl halides being very sensitive, and acid anhydrides left overnight can start to hydrolyze in just the water in the air. In this last video, we're going to look at the less reactive class 1 carbonyls, esters and amides. So we've finished discussion of the more reactive, water-sensitive class 1 carbonyls, where we have great leaving groups or good leaving groups. Now we're moving into the territory where we don't have really good leaving groups. The OR without protonation is not a good leaving group, and without acid conditions the amine will not be a good leaving group. So let's go ahead and look at these last 2 functional groups within the class 1 carbonyls that can undergo, in catalyzed conditions, acyl substitution reactions. So we're going to make these esters and the amides good leaving groups. We've already looked at acyl halides, acid anhydrides having great leaving groups, a halide, good leaving group, carboxylate, and we'll look at, when we look at esters and carboxylic acids together, we'll look at these 2 together. These are our last 3 that we'll talk about. Very similar reactivities between carboxylic acids and esters. Alright, and this is the last of our videos on acyl substitution. So let's look at esters hydrolyzed either in base or acid conditions. One will be acid catalyzed, the other one will be just base conditions because it's non-reversible. Catalytic conditions we have reversibility. So let's look at reversibility, where we have double-headed arrows all the way through the complete reaction in the acid catalyzed hydrolysis of an ester. Let me say that again. The acid catalyzed hydrolysis of an ester, where we have an OR group off of the carbonyl. Well, we know with every strong acid that's used as a catalyst, that's our first step, is to attack the acidic proton. So we do that with the partially negative oxygen and not the OR group, since this would be actually a donor, partially positive. And we have now a more reactive electrophilic site. We need that. We don't have a great nucleophile, and we need to increase the electrophilicity then of this carbon. We do that by protonating the oxygen, and by resonance there's a significant partial positive charge expressed here. We can then attack that partial positive charge, advance the pi electrons up to the oxygen, and we have our tetrahedral intermediate, our Ti, that is positive, because we have a oxygen that was neutral in water that is now attacked using its lone pair. It has 2 of them. Now it only has 1 of them because the other lone pair is now buried in a sigma bond onto this carbon that was in a double bond to the oxygen. So that's our Ti. And we have then in our next step a proton transfer, PT. We're just going to transfer the proton from this oxygen in the oxonium ion to the oxygen in the OR group to make a different oxonium ion. Now we have a new leaving group. It's not that this is a great leaving group without protonation, but with protonation we do have a good leaving group. And we don't transfer the proton just because it's thermodynamically favored. We do it so that we can make something new. It would have been just as easy to kick off water and reform the double bond between this oxygen and the carbon, but we would make something old. If we transfer the proton to the OR group, we get a new leaving group, and we can make something new. So I'm just going to show the product minus that proton. We're going to take that off in a subsequent step to this. We would have loss of that acidic proton. This is the acidic proton regenerated. Acidic proton regenerated. And that's that catalytic proton that's regenerated, and we would have our final product. The oxygen in a double bond to this carbon. The alcohol is off, and we would have our OH that was from the water that would now be on. We have made carboxylic acid from our ester, and this is completely reversible because these two groups, an OR and an OH, sitting off the carbonyl, give the same sort of stability to this carbonyl. So they, in short, these two reagents are similar in their reactivity in terms of the partial positive charge on the carbon within the carbonyl. Very similar. Now I know we have an acidic proton and the ester does not, but in terms of stability of products, there's not much of a difference in terms of carboxylic acid's energy and the ester's energy. So we can reverse this reaction. How would we do that? We would take all the water out and add a lot of add a lot of alcohol, and still have our drops or catalytic amount of acid to give us reversibility. All right, so that's acid catalyzed hydrolysis of an ester. If we're going from ester to carboxylic acid, acid catalyzed hydrolysis. And if we have a carboxylic acid and we're going back through the reaction with an excess of the alcohol and a minimal amount of water, then what we would call this reaction, looking the other way, going back towards the ester, would be acid catalyzed esterification. So really you get 2 for 1 here. You get a reaction, if you wanted to know frontwards, it's carboxylic acid formation. That would be called acid catalyzed hydrolysis. If we wanted to consider the reaction going backwards, since it's reversible, we would have acid catalyzed esterification. Now we can't have reversible conditions in base solutions. In fact, we don't even use the term catalytic conditions. We would have base conditions, sort of as it's saying here. Wherein we're going to take it for every one of these, we're going to make one new, very stable anion. Let's go through how this reaction would take place. Well, I know the most reactive, agent within this mixture of 3 is the fully negative oxygen in the hydroxide. That's where the reaction has to start. So there's no acidic proton here. We don't have this base conditions for hydrolysis of a carboxylic acid. It would just tear off the proton if there was one here. Since there is no proton, we're starting with the ester, we can have hydroxide or carboxylate formation from the ester. And this is just going to be called saponification. Taking a ester to a carboxylate, saponification. Let's show how that happens. So we would have attack using a strong base. Since there's no acidic proton here, we can attack to make the Ti, but in this case it would be negative. Tetrahedral intermediate, now that it's negative, we put a negative on this oxygen. The OH from the hydroxide is now attached, and we have the tetrahedral carbon here, sp3 hybridized. We're going to drive this down and kick off a new leaving group. Not a great leaving group, it's actually a bad leaving group. But this sets us up for a reaction that is hard to stop. If we make just some small amount of the following agents: carboxylic acid and a strong base, we have now a new strong base. It's the same basicity in general as a hydroxide. So we've really gone strong base to strong base. And if this was where we stopped, it would be reversible. But this is not where we stop. We have an irreversible reaction that I hope you can see. Strong base, carboxylic acid. strong base, carboxylic acid. Give you a second to look at that. What could we propose happens? Well, we know it starts here. The negative charge is most reactive. This is neutral. And we always go to look to a carbon that we could react with. Well, we could hit this, but it'd be going backwards, and maybe that's a little bit, I guess, less likely to happen, not only because it's a little more hindered, but also we're making something old. But if it can act as a nucleophile, that is, this negative can attack a partial positive carbon, always watch out for the other action. Action is just a base, ripping off a proton. I think we can do that. This proton, if we take that off, we make a carboxylate. A carboxylate, and I don't know if you've carboxylate anion. Carboxylate anions are very stable. We'd have this, of course, plus the alcohol. Carboxylate anions are very stable. When we have a negative on an O, well, you say, well, I had a negative on an O here and I have a negative on an O here. Well, the difference is we have resonance delocalization. It's really two oxygens that share that negative charge. So we have a very stable anion. Carboxylate anions are stable, more so than alkoxides or hydroxides, so this is irreversible. Once we make some small amount of this, game over. You're going to carboxylate. We're going to have the saponification of the ester, making of carboxylates. And again, when we finish this reaction, you could take and add an acid to protonate this oxygen once this was completely finished, and then we would be able to make, through saponification, carboxylic acids. All right, so that's acid and base hydrolysis of esters. We really have three reactions to kind of review. We have acid-catalyzed hydrolysis, acid-catalyzed esterification, saponification of esters to make carboxylates, and we could, if we wanted to in this reaction, then end with just acid workup to make carboxylic acids from the carboxylate. All right, one more before we get to the amides. What if we take an ester, not with acids or bases in water, but what if we take an ester with an amine? And we could use the amide form, the more reactive form of this, but we can actually just have an amine instead of having the negative form, the conjugate base of the amine, like the amide. We can use the amide too. This could also be used, but we don't need to use the more reactive form of the amine, the negative form of the amine. We can use just amine and have a slow reaction in solvent to form, I guess, the amide in terms of the class 1 carbonyl. So we don't have any acidic protons. There are no acidic protons to protonate this oxygen. So we're just going to propose that we in general have this as our leaving group. This is our nucleophile, and we know if we use a neutral nucleophile, in the end, one of those protons has to go to the leaving group. If we use a neutral nucleophile, we have to lose a proton, because if he's going to attack as a nucleophile, that is, hit a carbon and advance those electrons and go through the reaction to replace the leaving group, he's going to have to at some point lose a proton, because he would be left with a positive charge if we don't kick off one of those protons. Let's look at the mechanism in this, I guess, space below. We have the balanced reaction, leaving group replaced with a neutral nucleophile, to leave the leaving group off with hydrogen from that neutral nucleophile. But let's go ahead and show the mechanism. So we can propose initially a Ti that is Zwitter ionic, having a plus and minus charge, and we would have a very quick proton transfer. In this case, we don't have a great leaving group. This is not a great leaving group, and with acyl halides, acid anhydrides, we breathed in and breathed out as quickly as we could because we had good leaving groups, or great leaving groups. But with these reactions, we don't. This is not a good leaving group. So we can have some time wherein that OR sits and waits for this oxygen that went negative to be protonated, and then for some weak base, as these as the proton's being extracted, to help drive this reaction, have the lone pair come down and kick off a bad leaving group. Still have some, I guess, possibility of this occurring in solution, and it can. And we get a more stable carbonyl compound. So we have a more stable carbonyl compound. The amide is more stable than the ester. And we would just have a very quick reaction, irreversible, where this alkoxide picks up the proton to give us just the ROH and ammonia back that had been used in this sort of third step after we had attack, proton transfer. We can have this amine act as a weak base for just a short period of time to rip off the proton, allow this leaving group to come off, and then that leaving group can come back in the last reaction from this. We can have these two get together to make the alcohol and the ammonia. So I haven't shown that as a last reaction, but we can have regeneration of our amine so they can go back and continue the reaction over and over again. Now, typically mechanisms are not shown for formation of amides from esters and amines, because there are a lot of different ways we could have drawn that mechanism. It has to do with the fact that these tend to be fairly stable, either in the zwitterionic form, not so stable, but in this form, this is a fairly stable TI. Not a good leaving group. We don't have a lot of acidic protons here, so we can have a lot of different things happen from this point. So typically mechanisms aren't shown for this reaction, but we've just proposed one here that we could consider for the formation of a more stable amide. So we know thermodynamically this is a favored reaction. The amide is more stable than the ester. And we kick off the alcohol in the end, because that alkoxide will pick up that proton to make the alcohol and reform that amine. Alright, two more reactions we can take and go backwards. We said these are more stable versus a ester, but that's when we don't have any acid conditions or strong base conditions. If we just have a neutral amine, we can have a reaction just to make the amide, or use the conjugate base of the amine, and we can have a very rapid reaction to make the amide. But if we use acids or bases in water, in aqueous conditions, we can get a dynamic that's unique to the amides. Because of this nitrogen's inherent basicity to make ammonium ions, if we have some acid proton, for every one of these we can make not just NH3, but we can make ammonium ion. So this is, we'll treat it as acid conditions, but we know that this acidic proton will not be free. In the end, we'll have, for every one of these, we'll have one ammonium ion. So it's really not right to say it's acid catalyzed conditions. It's really acid conditions, because we're going to take a certain amount of acid, equivalent amount, and for every one of these, again, we'll have the amine binding that proton irreversibly. So I've shown the balanced reaction as if it was acid catalyzed, but really every one of these will be bound by that NH3 that's formed in the reaction. So this is still going to be our leaving group in the end. This is going to be our nucleophile. To substitute that, we're going to still have to lose an H from this water. It has to go with the NH2 group. But please know what drives this reaction, makes it irreversible, is that for every one of these, we're going to make not just NH3, but NH4+. Let's look at the mechanism. So we changed the description from not catalytic, but just acid conditions. We always protonate. The oxygen's partially negative, so we're going to protonate this oxygen. This nitrogen would be a great donor, partially positive. So we donate to the electrons to the oxygen. He goes and binds the proton, becomes full positive, and creates then a very electrophilic carbon that water can attack. And once we get to this point, we really open up this reaction to susceptibility to acids. This amine is now sp3 and fully basic. We have a lone pair that's going to quickly pick up the proton from the water that attacked, so we get a PT, proton transfer. Internally, this becomes now a good leaving group, GLG, not a great leaving group, but a good leaving group. So we can kick off that good leaving group, and that good leaving group is a good base. It's not a great base, but it's a good base, and we can irreversibly bind that, not catalytic proton, but equivalent proton. For every one of these protons in blue, we're going to make one ammonium ion. So we bury this reaction by taking equivalent amounts of acid to equivalent amounts of ammonium ion. So that's the mechanism for formation of carboxylic acid in the acid, hydrolysis of amides. Now let's look at base, and we'll be done. Base runs on a little bit different principle. It's not that we have a basic nitrogen we're going to pick on, but we have the chance to make the carboxylate anion because we're in aqueous conditions. So we can have the base, whatever that is, generate some hydroxide. So I'll just say whatever the base is in water, we're going to get some hydroxide. And the hydroxide is going to be the key agent. If that's used as a nucleophile to replace the leaving group here, well, we can see that setting up for the formation of the carboxylate, because we'd have carboxylic acid and a strong base. So we're going to say for every one of these, then, we're going to make one carboxylate. So we need equivalent amounts of this base, not catalytic amounts, equivalent amounts to make the carboxylate. So let's look at the mechanism. So we have an attack to make the TI, that's going to be negative. And if we have the loss of amide, this is a bad leaving group, but once formed, itty-bitty amounts of this forms in the presence of what's left, the carboxylic acid, we have a fast reaction down to the carboxylate. The carboxylate plus that ammonia, because this proton, being very acidic, will be picked up by the nitrogen to make ammonia and, again, carboxylate anion. And this is a much more stable negative charge in solution than the initial hydroxide, the negative O in the tetrahedral intermediate, and especially the negative nitrogen in this amide. So these react rapidly, making this reaction irreversible. This is the irreversible part. Alright, well, that's it. We've covered hydrolysis of amides, either picking on the nitrogen's basicity or picking on the possibility of making the carboxylate. Whenever you can make the carboxylate, it's going to drive pretty much all the reactions to carboxylate. You can't, in base conditions, if you can make a carboxylate in whatever reaction you're considering, you better watch out, because that may be more stable than any of your products. Carboxylates can drive reactions. So we can have driven acid-base reactions in water driven by the carboxylate formation, so amide, hydrolysis in base conditions. We've looked at our amide, hydrolysis in acid conditions, amide, hydrolysis in acid conditions, so acid conditions and base conditions. And we've looked at reactions of esters to make amides, higher energy carbonyl, lower energy carbonyl, so we're going downhill. And we can use a neutral amine to do that, to go downhill, because esters and carboxylic acids are a little bit more reactive than amides in general. So we can go down from an ester to an amide. And the last one, we looked at just the acid-base hydrolysis of esters, realizing that since these are equivalent in energy as far as carbonyls go, we can have acid-catalyzed hydrolysis or acid-catalyzed esterification. So we can go back and forth in acid conditions between carboxylic acid and ester. But we can have irreversible conditions if we want to go ester to carboxylate. We can have irreversible conditions. We talked about saponification. Well, that's a lot. I'm just going to end with this slide. Try to remember that the order of reactivity really follows this pattern. Acyl halides and hydrides are most reactive. Esters and carboxylic acids are similar in reactivity. That's why we can have reversibility between these two. The amide is the lowest energy class 1 carbonyl, and the only way we can really take advantage of getting out of this hole is by adding strong acid conditions and picking on the amines basicity, or having strong base conditions and picking on the opportunity to make carboxylates. We can dig ourselves out and get to carboxylic acid. All right, that's it. It's a little bit longer than I wanted, but I hope that helps, and we'll see you. Bye-bye.